classical control systems project presentation, where our project is the two-axis gimbal, and it was developed by me, Joao Fernandes, Sahil Jain, and Jaden Pinto. We did this under the guidance of Professor Dattatya Sawant, and we are from the semester 5 third year Mechatronics batch in the academic year 2025 to 2026. So now, this is the 3D design of the gimbal model that we have modeled in Fusion 360. Um, yeah, I will come back to this later, but this is the isometric view, the front view, and this back view. Now, the components we have used in the hardware of our project, the gimbal. So we have used the MPSTME sensor, which contains an accelerometer and a gyroscope. So we have only used the accelerometer sensor of this MPSTME to get the accelerations along x, y, and z to get our roll and pitch angles. The Arduino Nano we have used not to store code, but as a device that links our Simulink model to the sensors and the actuators. So now the sensor MPU650 is going to give data. This data will go into the Arduino Nano, and then we'll communicate it or to send it directly to our Simulink model, which is in our PC. And then the data after calculations, this data will then get sent to our servo, which is the actuator, via the Arduino Nano. This communication from the sensor to the Simulink model to the servo cannot happen directly. That is why you're using the Nano. Now we have zero PCB board. This is used to avoid the use of our breadboards and wires. This will make the project look more clean and also makes it compact. Then we have the 7.4 volt lithium ion battery. This is used as an external power supply to power the two servos, which work at a range of voltage range of 4.8 to 6 volts. We have used 5 volts because we are also powering the MPU6050 sensor, which has an operational voltage of maximum of 5 volts. That is its cap. Now to convert 7.5 volts to 5 volts, we use a step down converter, which is the LM2596 DC to DC buck converter. Now we also use two servos here. Why not one? So the SG90 is a plastic gear servo, and the MG90 is a metal gear servo. So these two servos, we are using two different servos due to their different torque outputs that we require. Now coming back to the 3D design model of the gimbal. So now the accelerometer, which are the MPU6050 sensor, the Arduino Nano, the zero PCB breakout board, the 7.4 cell battery, and the LM2596 all are going to rest in this base of the gimbal. The two servos are going to be resting over here and over here. The servo that is resting over here is going to be the roll servo. This roll servo is going to be the MG90, as it needs more torque output to hold this load, as you can see, this L-shaped load, which also houses the pitch servo and this platform, the L platform, on which the object is going to be kept. So now the servo that is over here, as I already said, is the pitch servo. This pitch servo, as the name suggests, it controls the pitch of our platform, and this servo controls the roll of the platform. Now, so therefore, this is just holding the L shape and the object itself. Therefore, we use a weaker servo, which is the SG90, plastic geared servo. Now, proceeding to the Simulink model. Now, the Simulink model, we have made it in Simulink, which is a tool provided by MATLAB. And in Simulink, we have used two libraries. One is the normal Simulink library, and the other is the Simulink support package for Arduino. From that package, we have gotten three blocks. We have gotten the MPU6050 inertial measurement unit sensor block, and we have got the two blocks of standard servo ride. Now the MPU6050 IMU sensor block, we have only taken the accelerometer values, and it gives out the accelerometer values in a 3x n matrix of AX, AY, and AZ along the n sample times. Then we use a demultiplexer to demultiplex this 3x n matrix into 1x n matrix of AX, AY, and AZ. Then we have A tan 2, This is A tan 2 is required to convert AX, AY, and AZ, or specifically for roll AX and AZ, and for pitch AY and AZ, into the roll and pitch angles respectively. And this is going to be in a range from minus 180 to 180. Now we use 180 by pi to convert this radian angle that is outputted by A tan 2 into degrees. Next, we use a discrete filter. This discrete filter is used to change the amount that the outputted angle, the amount that it depends on the previous angles that have been recorded and the current angle that is recorded. This this change, we can change the amount that it depends on these two different values by changing the constant alpha. This can be changed by defining the value of alpha in the command window of MATLAB. So, so now, for the alpha can only exist in a range from 0 to 1. So when it is closer to 0, the discrete time filter makes it so that the value that is outputted has more dependence on the previous values of the MP6050 sensor. And for higher values of alpha, it depends more on the current value of the MP6050 sensor. So from what we have found in our research paper from different tests, we have found that for higher values of alpha, since it depends on the current values that is being outputted by the MP6050, therefore it is very quick. It is very fast. But it is very jittery since the values from the MP6050 are not constant, they are very variable. So it will still cause it to be very jittery, but having quick response. But for lower values of alpha, it has a very smooth response since it only depends on the previous values that are given by the MP6050, and also the and also it is very smooth, as I already said, but it is very sluggish because it does not depend on the current values immediately. It keeps on depending on the previous values that have already been passed. Therefore, it has a sluggish response. Now, both of these are not good. The fact that it is sluggish, as well as the fact that it is jittery. So, we have gotten an alpha value of 0.3, which is tested to be a sweet spot between the two. Then we have our gain blocks +1 and -1. These are to, if we want to invert the angles that are being outputted, we can invert it by changing it from +1 to -1. Then we have the saturation blocks. These saturation blocks are to limit the values that are being sent from the from this whole from these whole rows from the MP6050 into the servers from the output that is given here 10 2 can have outputs from -180 to +180. But what useful output we require is only from +90 to -90. Why? It is because the servos only have only can operate from 0 to 180 degrees. Therefore, we limit it to only operate in a 180-degree range. Then we have the constant block that is being inputted into a sum. So this is to change it from -90 to +90 range into a 0 to 180 range that the standard servo write blocks can accept. So this is how our physical gimbal model looks after it has been printed. Now this is a video of the working gimbal model where, as you can see, this is the PC where I have MATLAB Simulink downloaded. This is the Simulink model, as you can see, the model that we had seen before. I will be running the model and then demonstrating how our gimbal works. As you can see on the platform of the gimbal, I have kept an eraser just to demonstrate the working of the gimbal, or tilting the gimbal along various angles and different orientations and showing that the eraser remains on the platform. It is being stabilized with the gimbal. So I switch on the I run the Simulink model. Then I demonstrate the working of the pitch servo, then the roll servo as I'm doing now, and then a combination of both. As you can see, the eraser did not fall, and that is our demonstration of how the gimbal works properly. Thank you very much.